towards attempting to land on the moon to return the United States to the moon for the first time in 52 years.
Nova-C uses an environmentally friendly mixture of liquid methane and liquid oxygen.
Incredibly challenging thing like landing on the moon forced us to innovate.
Intuitive Machines has built an entire space program to support these CLIPS missions. The company completed its lunar lander in a new facility at the Houston Spaceport, just down the street from NASA's Johnson Space Center. It's an autonomous Nova-C class lunar lander named Odysseus.
Lunar lander arrived at Kennedy Space Center in Florida back in December. Since then, teams have been integrating the spacecraft to Falcon 9's second stage in preparation for launch.
Go IM-1 and the Odysseus lunar lander.
Falcon 9 has successfully lifted off from Pad 39A at Kennedy Space Center. An incredible sight to see.
Odysseus lunar lander separation confirmed.
Our Nova-C lunar lander has successfully separated from the second stage of the launch vehicle, autonomously commissioned, and made first communications contact with Nova Control.
Our approach for landing is actually very similar to what Apollo did, which should be no surprise because the physics are very much the same.
Let's honor this momentous milestone and prepare for the challenges and triumphs that await us on our lunar journey. You're taking a live look into Intuitive Machines' Nova Control in Houston, Texas, where flight controllers are preparing to start the landing sequence for the IM-1 mission. Our mission and activity directors are sitting closest to the large monitor inside Nova Control, and they're supported by 10 additional flight controllers surrounding the circular Mission Operations Center. Good afternoon and welcome to our coverage of the descent and landing of the IM-1 mission. I'm Josh Marshall, Communications Director of Intuitive Machines.
And I'm Gary Jordan with NASA Communications. This mission is one of the first under a task order with NASA's Commercial Lunar Payload Services Initiative. Under Artemis, we're returning to the moon to conduct groundbreaking scientific discoveries and technological advancements. And this mission with Intuitive Machines is helping us to get there.
And Gary and I are at Intuitive Machines' facility here in Houston, just down the street from NASA's Johnson Space Center. Right now, inside Nova Control, flight controllers are monitoring our Nova-C class lunar lander named Odysseus ahead of its autonomous landing sequence that begins with powered descent initiation at 5:11 p.m. Central Time for a landing time at 5:24 p.m. Central. Right now, they're keeping an eye on the room's situational awareness tool called the Viz, which you can see on your screen now. The Viz is casted onto a large television in the front of Mission Control, so the activity director and the mission director can have the best view, Gary.
And the Viz is an animation representing real-time telemetry data feeding into Nova Control. Nova Control receives the data, runs it through Unreal Engine 5, and generates a visualization of the data. It's a useful tool for situational awareness and keeping track of what flight controllers expect Nova-C is doing in space. The white line points to the moon. The blue line is the past and intended trajectory. The yellow and red lines are pointing towards the sun and Earth, respectively. The different color cones you see at the top are the antenna arrays used for line-of-sight communication back to Earth. We'll show the Viz periodically throughout our coverage, up to about 12 minutes prior to landing. In these final moments before landing, the most reliable spacecraft data will be relayed through Nova Control audio loops.
And we're starting our coverage later than expected today as flight controllers continue to assess Nova-C's trajectory, guidance, navigation, and control. Nova-C maintained a low lunar orbit, but is in a slightly more elliptical shape. Last night, flight controllers performed a lunar correction maneuver burn to adjust the lander's orbit. This burn kept Nova-C on a trajectory to land in Malapert A, but moved our landing time estimates earlier by about an hour. Then today, flight controllers chose to exercise an additional orbit before starting the IM-1 mission landing sequence. This decision brought us to now, projecting a landing time of 17:24 Central Time. Intuitive Machines made the decision to reassign the primary navigation sensors from Odysseus's laser range finding system to use the sensors on NASA's navigation Doppler LiDAR.
This is a dynamic situation, and we'll update you later in the broadcast. Intuitive Machines still intends to land in the optimum lighting window, and the lunar correction maneuver performed last night eliminated the need for the planned 10-second deorbit initiation burn, which would have brought Nova-C from low lunar orbit into the descent phase. Nova-C's current trajectory has it continuing to decrease its altitude over the next hour until the braking burn called powered descent initiation.
Again, the landing time is expected at 5:24 p.m. Central Standard Time, 6:24 p.m. Eastern. The countdown clock at the top of your screen is counting down to the time that we expect to remove, and we expect to remove the countdown clock approximately 2 minutes before the landing opportunity. Getting to this moment, Gary, has been quite the journey, and it's lasted about 7 days so far since liftoff from Launch Complex 39A at NASA's Kennedy Space Center. Odysseus lifted off at 1:05 a.m. Eastern Standard Time from atop a SpaceX Falcon 9 rocket on February 15th. Approximately 48 minutes later, Intuitive Machines' Nova-C-class lunar lander entered a translunar orbit, a direct shot at the moon. In the following days after launch, flight controllers in Nova Control commanded engine firings to place the lander into low lunar orbit, approximately 100 kilometers or 62 miles above the lunar surface. The journey to low lunar orbit included firing the first liquid methane and liquid oxygen engine in space. This was called the commissioning maneuver. It was a full-thrust main stage engine burn with a throttle-down profile necessary to land on the moon. Over the last 24 hours, Odysseus has maintained its trajectory in low lunar orbit, waiting for suitable lighting conditions to begin its autonomous descent to Malapert A, the designated landing site for the IM-1 mission near the south pole of the moon.
Our joint coverage will follow Odysseus through its descent and landing on the lunar surface, carrying 12 payloads down with it. The mission is enabled under a task order with NASA's Commercial Lunar Payload Services, or CLPS. Here's more on this initiative under Artemis.
Our moon. It seems so close in the night sky, but getting there is really hard. But what if there was a way to change that? Only a few nations have successfully landed on the moon. As NASA sends astronauts back to the lunar surface, this time to stay, we will need to send science and technology instruments ahead of time to lay the foundation for human exploration. To make this happen, NASA is helping establish a commercial lunar economy. For the first time ever, there will be commercial delivery services to the moon. We are enabling American companies to send our payloads to the lunar surface for us. These delivery services will expand our capabilities for exploration, radically increasing the amount of science we can achieve. This high-risk, high-reward initiative will invest in and leverage the entrepreneurial spirit of American innovation to launch a commercial lunar marketplace, advancing technology and exploration for all of us. With this never-before-seen streamlined access to the moon, we will be able to make novel measurements and develop technologies that scientists have long wanted to do on the lunar surface. And as this new industry matures, this commercial delivery service for NASA and other customers could expand beyond the moon to other destinations in our solar system. And we can learn to live on another world because we are explorers.
CLPS is an important pathway towards long-term exploration of the moon and part of NASA's Artemis missions that will establish a sustainable presence in the lunar vicinity and prepare humans for missions to Mars. For more on how this fits in with the greater plan, let's head over to NASA's Leah Cheshire, who's just down the hall. Hey, Leah.
Thanks, Gary. I'm here with Joel Kearns, NASA's Deputy Associate Administrator for Exploration. Thanks so much for being here, Joel.
Oh, thank you, Leah. It's great to be here on Landing Day, which is the culmination of about 5 years of work by Intuitive Machines Corporation.
Yeah, we're really excited, and we want to know a little bit more about NASA's goals for the CLPS initiative.
Okay. So, most basically what we want to do is we want to have American companies take NASA equipment and scientific investigations all the way to the surface of the moon and not have to have NASA do that ourselves. NASA is really good at doing robotic space science missions, whether that's the James Webb Space Telescope or it's the Mars rovers. But when we knew about 5 or 6 years ago that we would start going to the moon to do science and exploration investigations. We knew we'd be going back every year, so we turned to industry to see if they could actually take us to the moon instead of us having to do it ourselves. And that's how we came up with commercial lunar payload services. There's three objectives for commercial lunar payload services, or CLPS. One is that we want to do great science on the moon. The second is we want to test out technology and engineering for future human exploration in Artemis. And the third is we want to generate a group of companies that are highly skilled in doing these robotic lunar landings so that we can use them as part of our Artemis initiative.
Well, let's talk about that a little bit more. How is CLPS beneficial to the Artemis campaign?
Well, a number of different ways. For example, we will do science at the South Pole with our astronauts in Artemis, and also with robotic explorers. They'll be brought down on CLPS. But we're also going to use these robotic landings, these commercial robotic landings, to do science at places where we won't initially send astronauts. We can use them, for example, this intuitive machine mission that's going on today that'll land in the South Pole region will be one of the first forays into the South Pole to actually look at the environmental conditions to a place we're going to be sending our astronauts in the future. That is, what type of dust or dirt is there? How hot or cold does it get? What's the radiation environment? These are all things you'd really like to know before you send the first human explorers. I'd also say that in the future, when we are flying humans to the moon as part of Artemis, we can use commercial services like CLPS to pre-stage equipment or other cargo so that they're waiting for the astronaut explorers when they land.
And this is an entirely new approach that uses a privately developed lunar lander. What are some of the most important takeaways on risks but also benefits of a model like this?
So when industry came to NASA about 6 years ago and said, we could do this for you as a service, what they said was they thought it would be less expensive than if we did it ourselves, that they could do it faster than we could set up to do it, and that they could do it more frequently, that they could do more than one mission, every year or two. And so far we've seen is that looks like that's going to be true. What we're waiting to see, such as with the mission today, is can they actually do this incredibly difficult thing? Can they really land on the surface of the moon robotically? This is something which is extremely challenging and difficult to do. The moon has no air. You can't use parachutes or wings to slow down. You have to, in effect, ride a rocket engine all the way from orbital speed, thousands of miles per hour, all the way down to a very soft touchdown speed to land in this place, which is very rough, pretty rugged, in really unusual lighting and communication conditions. So this is not an easy thing we have asked these companies to do, but if they're successful, the upside for American exploration is just so great, we have to try it.
Yeah, absolutely. Those are important distinctions. And thank you so much for joining us here today, Joel. With that, we're going to toss it back to Josh and Gary to preview the landing sequence.
Thanks, Leah. We're following along with Novacy's descent toward the lunar surface. The lander is continuing to decrease its altitude until the powered descent initiation, an 11-minute braking burn that sets Novacy up for the final moments prior to touchdown. That time of ignition for PDI, or powered descent initiation, is 5:11 p.m. Central Time, 6:11 p.m. Eastern. The entire landing sequence is autonomous, meaning the lander is in control of every milestone required for a lunar landing opportunity, Gary.
And completing a soft touchdown comes with challenges unique to, say, landing on the Earth or Mars, because there's no atmosphere.
Gary, it's an entirely different playbook as we've seen this dynamic situation play out today. Let's take a look at the IM-1 mission's complete trajectory approach as of launch. The Intuitive Machines IM-1 mission is sending commercial and NASA payloads to the lunar South Pole region on an uncrewed robotic Nova-C-class lunar lander called Odysseus.
The lander is the tip of the iceberg, and what's below that is the full program that is on a miniature scale, very similar to what the Apollo program had.
The IM-1 flight path mirrors the historical achievements of Apollo 2, starting with separation for the launch vehicle on a direct shot at the moon.
That trajectory is basically like throwing a fastball that is going to hit the moon 6 or 7 days later, like an outfielder stretching out to grab it.
The first 4 days are dedicated to flight controllers in Houston firing the lander's 3D printed liquid methane and liquid oxygen engine to make small course adjustments to hit its orbit target around the moon. This particular coordinate system is called the B-plane.
You can think about the B-plane kind of like the backboard of a basketball goal. And you basically know when you shoot hoops that if you can get the basketball in the square on that backboard, it's going to go in. And the B-plane for astrodynamicists is very much the same thing.
With the B-plane on target, Odysseus is prepped for a critical autonomous maneuver on the moon's far side. This critical burn maneuver is completed in the blind, with the moon blocking direct communications back to Nova Control in Houston.
Once we get around the moon, we have on the day side of the moon, the sun heating us from one side and reflected infrared light off the bright moon warming us on the other. Then we plunge into night, and now we're cold on both sides. It's very tough.
About an hour before landing, flight controllers command Descent Orbit Insertion, or DOI. This is a main engine firing to slow the spacecraft so its altitude drops from 100 kilometers to about 10 kilometers above the lunar surface. After DOI, Odysseus coasts for about an hour before starting its final approach.
And then we reach a point called powered descent initiation. The guidance system on board makes the decision to activate the main engine at very close to full power.
Cameras and lasers are feeding information to the lander's navigation algorithms, which provide guidance, navigation, and control. With a safe site identified, Odysseus enters a 3 meter per second descent, then down to 1 meter per second for the last 10 meters to the lunar surface. Now, the lander is using an inertial measurement unit, which is similar to a human inner ear that senses rotation and acceleration. Flight controllers expect about a 15-second delay before confirming the ultimate milestone, softly landing on the surface of the moon.
And I can tell you just from doing our simulations, that's the longest 15 seconds you'll ever experience as you wait for the final light to turn green to indicate that you've landed on the moon.
Approximately 12 minutes before our landing opportunity, we're going to show this animation of the landing sequence to describe the lander's autonomous operations, starting with powered descent initiation, or PDI. During this maneuver, Odysseus must reduce its velocity by approximately 1,800 meters per second. You can think of it as a braking phase. Then, the lander pitches upright using its main engine with the Hazard Relative Navigation, or HRN, now being fed by NASA's NDL sensors, facing toward the area where the lander intends to touch down. At this point, HRN will autonomously scan the intended landing site for a safe landing area. Then, the lander's guidance, navigation, and control system commands Odysseus to a point approximately 30 meters above the designated landing site, and the lander goes into a vertical descent followed by terminal descent. Intuitive Machines created Nova-C for the CLIPS initiative and commercial enterprise with the goal of creating a lunar economy.
And Nova-C is Intuitive Machines' first autonomous spacecraft. Nova stands for new, and C is the Roman numeral for 100, the lander's approximate payload capacity. With that, let's learn more about the Nova-C class lunar lander.
This IM-1 mission lander is named Odysseus. The name was nominated by Assembly, Integration, and Test Engineer Mario Romero after the Odyssey and its epic voyage across the daunting, wine-dark sea. Including landing gear, Odysseus is 4.6 meters wide, and with its top-deck solar array, it's 4.3 meters in height. It's a taller design that accommodates payloads and the lunar South Pole lighting conditions. Its hull diameter is 1.6 meters, with payloads affixed to the entire exterior of the lander, making its total payload capacity approximately 130 kilograms. The lander weighs 675 kilograms, but packs on weight when loaded with fuel. Odysseus uses composite helium tanks to pressurize its liquid methane and liquid oxygen main engine that can throttle down to perform its final descent to the lunar surface in one continuous burn.
Intuitive Machines' IM-1 mission is supported by NASA's Commercial Lunar Payload Services Initiative, which allows rapid acquisition of lunar delivery services from American companies. The instruments on board advance capabilities for science, exploration, and the commercial development of the moon. Commercial companies were challenged to come up with their own way to design and fabricate a lunar lander and conduct operations. For this commercial mission, Intuitive Machines elected to support the communications between the spacecraft and Nova Control through its own private ground-based network. And it's not the first time Intuitive Machines used this network in deep space.
Well, that's right, Gary. NASA worked with Intuitive Machines to perform technology demonstration of this capability on NASA's Artemis 1 mission, which helped us verify the network for operational use during this CLIPS mission. The Lunar Data Network, or LDN, uses ground-based networks to communicate into deep space, so we could lose signal while Nova-C is on the far side of the moon. However, the trajectory of the lander's low lunar orbit does allow for near continuous line of sight with Earth and ground station coverage. Let's head over to NASA's Leah Cheshire to learn more about this network. Leah.
Thanks so much, and I am here now with Trent Martin, the Intuitive Machines Senior Vice President of Space Systems. Thanks for joining us, Trent.
Thanks.
We're here to talk a little bit about the Lunar Data Network. This is a private deep space network, belongs to Intuitive Machines. How does it differ to have this commercially available space network, and how is that different from NASA's Deep Space Network?
So when we first got onto the Commercial Lunar Payload Services contract, we were trying to find a way that we could get our data from our landers back to the Earth. We were worried that the Deep Space Network, which is often oversubscribed, particularly with James Webb Space Telescope now, that we would have limited time. So what we did was we created a network of large dishes across the planet that allow us to take our data from the moon and deliver it down to the Earth.
And we initially tested this out during the Artemis 1 mission. So how did Intuitive Machines work that out?
Yes, we worked a reimbursable Space Act agreement with NASA to allow us to test our network not only with Artemis at 430,000 kilometers, but also with the Lunar Reconnaissance Orbiter, as well as the GOES satellite.
Okay, and what are the goals overall for Intuitive Machines? How do you want to expand this LDN coverage?
So we believe that as the market expands at lunar distance, many people will need the capability to send data back, particularly if you're operating spacecraft on the backside of the moon. You need to be able to have a relay satellite. So we're going to put relay satellites in orbit to complement our ground-based systems, which are, again, large dishes all over the world. And by doing that, we'll be able to hopefully create a market for that data system from lunar space.
Okay. Is there anything else that you want to share that has gone into the development of this network?
It's really exciting. We've actually been using it this week once we launched Odysseus into space, and we're taking it to the moon. We've been using this network that we tested with NASA systems for the whole week, and it's been incredible to see it work and see it in action. We have a long ways to go with it. We need to add additional satellites to the system so that we can relay data back from the moon. But we think it is the future of humanity in lunar space.
Thanks so much. It's really exciting to see this in action. And we are just minutes away from acquisition of signal to confirm deorbit insertion. So we're going to send it back over to Josh and Gary to follow along with the operations.
Thanks, Leah. That Lunar Data Network information feeds into Nova Control's communications and ground network console screens. It's just one of many different screens that are used by the flight controllers, and we want to bring you closer into the mission and into our Mission Operations Center. Let's take a look at what flight controller teams are seeing now. This particular screen is called the Deorbit Descent and Landing, or DDL screen. This screen is primarily used by the mission director and landing system experts. It's used primarily while Nova-C orbits the moon and through landing. The top right images of the moon are called the lunar tactical view. When the dots turn red, the lander is on the far side of the moon, and green is on the near side. The line is the tail where Nova-C is, with each dot representing 10 minutes of elapsed time. The acceleration sensed portion of the screen shows raw acceleration values from Nova-C's inertial measurement unit. This is used a lot during burn maneuvers and is a more robust way of measuring acceleration over time with the ability to look back at what has happened. For some reason, flight controllers have lost data. Finally, the column on the right is a received, accepted, edited, and failed pre-checked, or RAFE chart for short. When each of these lines are on top of each other, that's a good indication that Nova-C's navigation system is in good health. That's because every measurement Nova-C makes must be received, accepted, edited, or failed pre-check. The failure is a possible outlier of data that the lander's computer automatically knows is bad information. Collectively, the DDL screen is one of many data displays that flight controllers are monitoring to successfully navigate Nova-C to the lunar surface.
Data visualization is an essential component for flight controllers who need to process this data for real-time decision-making in Nova Control. Now again, we're following along with the flight control teams here in Nova Control prior to the next critical steps, including activation of the navigation Doppler LiDAR to provide guidance, navigation, and control for the landing phase. This is expected around 4:45 p.m. Central Time. The next critical milestone is powered descent initiation at 5:11 p.m. Central. This burn is the first in a sequence of maneuvers that starts about 12 minutes prior to landing, or about 50 minutes from now. Nova C is, of course, landing on the moon as a delivery truck for the scientific instruments and technology demonstrations on board. There are 12 total payloads, 6 of which are NASA's. Let's review a few of those payloads as we continue to descend towards the lunar surface. First is radio observations of the lunar surface photoelectron sheath, or ROLSES. ROLSES will employ 4 antennas and a low-frequency radio receiver system to determine the density and scale height of the moon's photoelectron sheath, a very thin layer of electrons above the surface of the moon, and will also detect solar radio bursts, radio emissions from Jupiter, dust impacting the surface of the moon, and how radio noisy Earth is.
An exciting radio telescope is going to be placed on the moon. It is called ROLSES. It stands for Radio Wave Observations from the Lunar Surface of the Photoelectron Sheath. It's going to detect all kinds of radio emission that is falling on the moon. Right now it is close to solar maximum, so the sun is producing a lot of coronal mass ejections and radio emission associated with them, and we can detect these radio bursts from the sun. Characterization of the radio environment of the moon is very important. It has not been completely done, and therefore ROLSES will be able to contribute in identifying various sources of radio emission on the sun. If you're setting up an observatory on the moon, we should know what kind of radio interference we get there.
The Laser Retroreflector Array, or LRA, is a collection of 8 retroreflectors that enable precision laser ranging, which is a measurement of the distance between the orbiting or landing spacecraft to the reflector on the lander. LRA is a passive optical instrument that will function as a permanent location marker on the moon for decades to come.
This is a little mirror that's aiming at you all the time, regardless which way you're looking at it. My name is Xiaoli Sang. I'm a LiDAR instrument scientist. It's a small retroreflector mounted on an aluminum shell on the intuitive machine landers. When you shine laser on it, it reflects right back at you. The purpose is to have a precise fiducial marker on the landers. It serves as a landmark for future missions if you want to go back and land it there.
Stereo cameras for lunar plume surface studies, or SCALPs, will use a suite of 4 cameras to capture stereo and still image data of the dust plume created by the lander's engine from when it begins its descent to the lunar surface all the way down through engine shutoff.
SCALPs is an array of small cameras that will be placed around the base of a lunar lander and collect imagery during the descent and landing of the vehicle. Using a technique called stereophotogrammetry, we can use those images to reconstruct a 3D shape of the ground. As the lander comes down, its hot engine plumes will interact with the surface. Our cameras will begin acquiring images from before this interaction begins until after the vehicle has landed on the surface. The SCALPs cameras will specifically be looking at the overall crater formation and erosion of the ground due to the rocket plumes. The final stereo images, which will be stored on a small onboard data storage unit, will be transferred to the lander and then downlinked to Earth, where we can use them to reconstruct the overall erosion volume and shape of the ground. With the Artemis program, we plan to establish a sustained lunar exploration and try to land multiple payloads in close proximity to one another. SCALPs data will be a critical part of understanding these phenomena and improving our computational models to inform these future landings.
Radio Frequency Mass Gauge, or RFMG, is a fuel gauge used to measure the amount of propellant in spacecraft tanks in a low-gravity space environment. Using sensor technology, RFMG will measure the amount or mass of cryogenic propellant in Nova C's fuel and oxidizer tanks, providing data that can help predict fuel usage on future missions.
I'm Greg Zimmerly, the principal investigator for the Radio Frequency Mass Gauge payload. This instrument is a space-age fuel gauge. We're going to use it to measure the amount of cryogenic propellant in the Intuitive Machines Nova-C lander propellant tanks. These propellants are very cold. They're at about -300 degrees Fahrenheit. Now we're integrating the instrument onto an actual lunar lander. Future lunar missions, like those in the Artemis program, will likely also use cryogenic propellants and have to store those propellants in space for long periods of time. So having an instrument like this that can measure the propellant in the tanks in low gravity will help future lunar missions know how much fuel is in the tank at all times.
Now we'll discuss two more NASA payloads, Navigation Doppler LiDAR, or NDL, and the Lunar Node 1, or LN1, later during our broadcast. We'll have a special guest later in the broadcast to talk NDL upon its activation during descent. And Josh, we did get word that some of the processing of the optical images from NDL are already performing. They did some checks, and they're performing very well. Now, a common theme you'll find among the NASA payloads on IM-1 is helping to demonstrate technologies and our understanding of the lunar landscape that could very well improve operations for landing on the moon in the future. From understanding the environment to precision sensors to literal beacons, the technology on IM-1 will help guide technologies and operations for future lunar exploration.
And Gary, with CLIPS as a springboard of innovation, Intuitive Machines designed and developed its complete lunar program to help support CLIPS and carry out the essential part of that directive, which included calling for the commercial development of the moon. Back in 2018, the U.S. government declared the moon of strategic interest. At that time, few companies and institutions were working on payloads designed for the moon because no one had been to the lunar surface in over 50 years. Gary, in the time it takes to get an undergraduate degree, 6 commercial entities created payloads for the IM-1 mission. We'll view all of them as pioneers helping shape this brand new lunar economy.
And Josh, a true lunar economy should not have just NASA as a sole customer. NASA's CLIPS initiative encourages a model where NASA is just one of many customers. And this is an important element to ensure that this model of transporting incredible science and technology instruments to the lunar surface is a sustainable and robust one.
Well, it's important, and Gary, it's also promising in this situation. The commercial interest for delivering science and technology demonstrations continues to grow. As of our third planned mission, we're seeing more and more non-CLIPS payloads from both domestic and international companies and institutions, which are driving us towards a future, maybe completely commercial mission to the moon, possibly as soon as our 4th mission.
Well, even on IM-1, there is a variety of unique commercial payloads. It's a good snapshot of out-of-the-box ways to think about what the moon can offer.
Well, that's part of the challenge. Beyond just creating the capability to land on the moon safely, we had to look toward a new emerging ideas and find innovative ways that may add value on Earth and spaceflight. Let's learn a little bit more about those payloads and the lunar lander attempting to make history.
The Nova-C was our version of a liquid oxygen, liquid methane lander, and we went about imagining that into existence.
Intuitive Machines' Nova-C class 3D printed engine took its first breath of liquid methane and liquid oxygen in 2018 on an airstrip at Ellington Airport in Houston, Texas.
We didn't have enough money for a facility with blast walls and water suppression or water deluge, so we had to test outside in the environment of Houston, where the temperature is about 100 degrees and the humidity is like the same, and we have an 18-hour day rolling out to the runway. It was brutal. But we did it to get the critical test engine data we needed to build our own engine.
Designed, manufactured, and controlled in space by Intuitive Machines, Nova-C's structure is primarily carbon composite.
We needed to build the lightest weight structure we could. That meant honeycomb aluminum core with composite face sheets, composite struts, and most importantly, linerless composite propellant tank. Man, what a challenge that was.
Between the engine, carbon composites, software, and electronics required to build a Nova-C lunar lander, it took an incredible amount of touch labor to get to the launch pad.
We worked very closely with San Jacinto Community College to create a certification course for technicians. where they would take these certifications. We then in Intuitive Machines would give them an internship and test them out in the workplace. And anyone that showed the aptitude to be a really good technician, we hired on the spot.
Nearly all of the lunar lander's payloads are mounted to its exterior, including 6 NASA-provided payloads that will help lay the foundation for Artemis missions. Embry-Riddle Aeronautical University's EagleCam, designed to deploy off Nova C right before landing to take third-person perspective images. The International Lunar Observatory Association's camera system, mounted at exact angles that could capture images of the Milky Way from the lunar surface. A data center technology demonstration by Lone Star Data Holdings, and Omni Heat Infinity, Columbia Sportswear's thermal reflective insulation used in many of their outdoor products, will help protect Nova C from extreme temperatures in space.
They've got brilliant ideas, and if we can help facilitate those startups to help build this economy, I think that raises all boats, and it's as serving as the transportation leg to the moon, we're happy to accommodate those kinds of companies.
Now, the lander and our payload customers require command and control in space. Intuitive Machines' Mission Operations Center provides both of those elements. It's called Nova Control, Nova being the name of our lunar lander class, and Control being the nerve center of our entire lunar program. Its unique circular design fosters a collaborative environment where flight controllers and customers may make agile decisions. Let's take a live look.
Yeah, and inside that flight control room, Josh, it's important to note that these are not the only teams that have been in this room over the past 7 days. This is staffed 24/7 inside in Nova Control here. There's red, white, and blue teams that support this mission.
Gary, the mission required 24/7 operations. We're somewhere in between the 7th and 8th day. This has been 3 teams, red, white, and blue, working 8-hour shifts, which really turned into just about everybody working 12-hour shifts each. In addition, there's another team, the gold team, that's running problems and solving solutions that are coming up in the future. And at this moment, we talked about this being a dynamic situation, using 2 of NDL's lasers to feed into our HRN and TRN cameras to provide a landing solution. Every asset available out of all of these teams is on hand right now to solve these intractable problems and take the best shot at the moon we possibly can.
It really took a team to solve some of these. As you mentioned, a dynamic situation. Now, you talked about the design of this room, fostering that collaboration. It's a little different from what I'm used to over at the International Space Station Flight Control Room, where you have consoles that are facing towards large screens. What exactly is the logic behind this particular design?
Really, we wanted to get everybody together into where we're a small company. There's not a lot of us. Agility is our strong suit in this situation, and this room really suited us. It's a situation where we can put our payload customers inside the center, or let's say we need to bring in operators who have knowledge of the things that need to happen in the future that we haven't quite touched on as a team, but you can insert those folks into the center of this room, make quick decisions, respond to problems, and that's really the way that we see tackling some of the hardest challenges in the world. And certainly right now for us, this is one of the hardest challenges on the moon, most certainly.
Which we are saying absolutely, and it takes everybody in this room, and everyone has their respective roles, just like we see with any spacecraft. Each of these individuals provides insights into a specific spacecraft subsystem.
And the captain of this whole thing is usually the mission director. In this case, this is Blue Team. That is Dr. Tim Crane. He's our co-founder and chief technology officer, serving as mission director today. Now, flight control operators continue to monitor Nova C's performance. Operationally, we're still counting down to PDI ignition at 5:11 p.m. Central Time and landing at Malapert A at 5:24 p.m. near the south pole of the moon. For more on Malapert A, let's head over to Leah Cheshire. Leah?
Thanks so much, and I am now here with Ben Bussey, Intuitive Machines Chief Scientist, to talk about Malapert A. Thank you so much for joining us, Ben.
It's great to be here.
Now tell me a little bit about this landing site. Why was it chosen? What sets it apart?
So the most important factor when selecting the landing site was to find a good, safe site for Odysseus to land. And we're landing in highland terrain near the poles, and that was a fun challenge for the team. But we think we found a good, large, safe area free of big boulders and craters. The other key factor was to try and land in the south polar region of the moon. If you know, NASA, through the Artemis program with their international partners, will be sending humans to the moon in this decade. So the goal was to find somewhere in the south polar region that was large and safe, and we sort of think just outside the rim of Malapert is sort of a Goldilocks location that will allow all the payloads to get the data that they want to get.
And you talked for just a second about that lunar highland material. That's what we believe Malapert A to be composed of. What is really interesting about the lunar highlands?
So if you look at the moon, you will see bright and dark regions, and the dark regions are lunar mare, which are old volcanic flows. The bright regions are mountains, are the highlands, which actually represent the original 4.5 billion year crust of the moon. So they're scientifically very interesting. They're also the same geology that the crew will visit. And so we want to go and get the first data of the highlands near the poles. And so we have one of our instruments, for example, is SCALPS, and NASA likes its acronym. So it's the stereo camera for lunar plume studies. And so that camera, which is 4 video cameras, will image the dust of the highland terrain right before we land. And so we will learn how it behaves as landers come down. So as we start to put multiple things near the poles, we know how far away we have to land.
And we know that there are some interesting conditions for these areas in the lunar South Pole. That can be lighting, that can be communications, terrain itself. So what can we expect at Malapert A?
So yeah, as you get very close to the poles, the lighting and communications becomes very challenging. And so for IM-1, we've gone to about 10 degrees, about 300 kilometers from the pole. And we think that's a good location because it's the closest to the pole that anyone's landed. But for example, we've chosen a site where you can see the Earth all the time, which is obviously communications being a key challenge. Whereas for IM-2, our second mission later this year, we'll go even closer to the pole. So for example, one of the things that we can study is, while we see the Earth all the time, it's still close to the horizon. And one of the things that communication engineers want to know is how communication is affected when the Earth is really close. So that's one example of something we can do in support of Artemis.
Well, thank you so much for joining us here today, Ben. That's all the time we have right now. We're going to send it back to Josh and Gary to talk a little bit about the landing sequence.
Thanks, Leah. Yeah, Malapert A is a fascinating satellite crater to Malapert, a crater only 300 kilometers from the moon's south pole. The site is named after Charles Malapert, a 17th century Belgian astronomer. The area around the landing site is believed to be made of lunar highland material, similar to Apollo 16's landing site. Apollo 16 was the first Apollo mission to visit the lunar highlands in an area called Descartes. Scientists believe the highlands offered insights into the moon's early history. The Descartes landing site turned out to be a source of rich scientific information. A large sample of rock called anorthosite was recovered from Descartes, which solidified more than 4 billion years ago during the moon's formation, when the outer regions were still molten. The IM-1 mission is carrying NASA payloads that may help better characterize this important scientific landing site for future Artemis missions.
And Gary, we were originally targeting from NASA Oceanus Procellarum. It was a lunar mare in the region of the near side of the moon. The decision to move from the original landing site in Oceanus Procellarum was based on the need to learn more about terrain communications near the lunar South Pole, which is expected to be made up of some of the best locations for sustained human presence on the moon. Landing near Malapert A also will help mission planners understand how to communicate and send data back to Earth from a location that is low on the lunar horizon.
Now we're coming up on the NDL activation. We have more information about how Intuitive Machines flight controllers intend to land on the moon using this NDL, NASA's Navigation Doppler LiDAR.
And Gary, since choosing to orbit the moon one more time, flight controllers have been working to resolve a challenge with the lander's laser rangefinders assigned to the terrain relative navigation and hazard relative navigation cameras. Those provide landing solutions to Odysseus. The lasers are intended to determine altitude and horizontal velocity, but the ones on the lander right now are not working.
These are essential measurements required to land on the moon. And while Nova-C's laser rangefinders are not operable, NASA's navigation Doppler LiDAR sensors are.
So during the last 2-hour orbit, flight controllers have been loading software patches and resetting the lander's guidance, navigation, and control system to use 2 laser beams from NASA's navigation Doppler LiDAR as primary navigation sensors to land Odysseus.
That's right. And we're coming up on the timeline for when Nova-C is about to begin the activation of NDL. This is a 3-step process from powering on, becoming ready for operation about 5 minutes later, and then integrating those sensors with Nova-C's terrain and hazard relative navigation cameras ahead of Nova-C landing. So while we wait, let's learn a little more about NDL.
So the Artemis program has taken NASA back to the moon, and everything that goes there, including the instruments and people, must be flown there safely and landed there precisely. So the landing phase of that task is one of the most critical aspects of it. NDL is a LiDAR instrument that is used to enable that capability. It uses light in the same way that sonar uses sound. For NDL, we have 3 telescopes where light would come out of the telescope, hit the moon's surface, and some of that light will be reflected back. These telescopes are mounted on the outside of a vehicle so you get a clear view of the ground as it's coming in for a landing. In the Apollo era, large radars or astronauts using their eyes looking out of a viewport were used to help land the vehicles. NDL is going to have to take the burden off of the crew with a much smaller, lower power, and more accurate instrument.
And we just got an update from one of the flight controllers that the HRN and TRN cameras assigned to Nova-C are still nominally processing images using 2 of those NDL lasers. Quite the feat, Gary.
No, it's absolutely incredible and a very important milestone to reach. Now, with that understanding, let's learn more about how this technology is playing an active role in this dynamic situation. Let's head over to Leah Cheshire. Leah?
Thanks so much, Gary. I'm joined now by Prasanth Desai. He's NASA's Deputy Associate Administrator for the Space Technology Mission Directorate. Thank you so much for being here.
Grateful to be here.
So let's talk a little bit about the novel landing technology that is NDL. Can you explain that to us?
Yeah, so NDL stands for Navigation Doppler LiDAR. And one of the challenges for doing any space missions is knowing where you are and trying to figure it out, right? And so we're looking to develop newer and newer capabilities that we can do that more precisely and that take up less volume and mass on the spacecraft so that you can have all the available payload mass for instruments and other scientific things that we're trying to do. And so this is the next generation of a new capability where we're trying to go from the traditional measurement using radar to a laser-based system. And so that's what this navigation Doppler LiDAR will be doing, is sending out 3 laser beams to try to get the velocity measurements in the lateral direction as well as the vertical direction.
So when it comes to NDL, what are some of the challenges we expect to see when using this technology?
So we've tested it on the ground in a number of platforms, from helicopters to landers here on the surface on the Earth to test this out. But this is the first time we're going to test it actually in the space environment on a lunar surface, right? And so we will see how that different environment will really affect the systems, right? And so one of the things that we would really like to know is what how the pulse comes back after they send the laser, and how it reflects back to the system, how long it takes to process, and how it will help define the solution to figure out the trajectory to go down to landing on the surface.
Now, this technology has become a little more critical for today's mission, so can you talk about how NDL is now being used in today's landing?
Right, so we put this as a tech demo with tech demonstration as a test. Right? We weren't planning to use it in line with the actual mission coming down to the landing, but now we are. So basically it is now the primary system to help provide the velocity and altitude information so that the lander can land safely on the surface. And that's important because as the lander comes close down, we don't want it to tip over. And so we need to get an understanding of the vertical velocity so it knows how much thrust to slow down, but also the lateral velocity, because if it comes down sideways too much, it can tip over and fall. So by knowing the velocity, the lander can decide exactly how to come down and hover, basically slowly to come down, and that's why it's really important to do this testing. But here we are today, we're going to try it for the first time in line, and so we're very excited for the mission.
Yeah, a demonstration totally in action.
Yes.
So just very briefly, there are 2 other tech demos on this mission. Can you cover those very quickly?
Yeah, so 2 other things that we're trying to improve on is one, radio frequency mass gauge, which is to try to get a measurement of the fuel that's on any system, any spacecraft. One of the things about low gravity is the propellant doesn't settle down, where like in a car gas tank, it's on the bottom so you can measure it easy. In space, it floats. And so how can we do that so we know how much propellant there really is? And then the other one is scalps. One of the things that as it lands, the thrust is going to throw up all this ejecta of the lunar regolith thing. And so we have 4 stereo cameras that are going to take images of that and get data so that we can improve our modeling, so that in future landings we can make them more safer and things like that. So we're using that as a technology demonstration as well to improve future landings to make them more safer.
Well, thank you so much, Prasanth. It's really been great speaking with you, really exciting stuff. And for now, we're going to send it back to Gary and Josh.
Hey, thanks, Leah. Nova C is a little less than 55 kilometers from the lunar surface and about 20 minutes to powered descent initiation, a critical maneuver that marks the beginning of Nova C's final moments before touching down on the lunar surface. It's no secret that landing on the moon is challenging. Countries around the world have attempted this incredible feat, some successful and some not. Of course, the United States has landed on the moon many times, most notably during the Apollo program. But this may be the first landing by a U.S. commercial company enabled under NASA's CLIPS initiative. Ahead of these important milestones, let's discuss the challenges of landing on the moon through CLIPS. Take a look.
Landing on the moon is hard. We're going back. Under this Artemis program, we're going to be sending humans to the moon for the first time since Apollo. So ahead of humans, we want to get up as much science exploration and technology experiments as possible.
So CLIPS starts facilitating a lot of the early science, the things we want to learn before we even send humans. CLIPS stands for Commercial Lunar Payload Services, CLPS.
The services part is the key element. Ordinarily, when NASA delivers a payload to the surface of the moon, they do it with a commercial partner, but NASA controls the building of the vehicle. Now, we're buying the service of delivery of our lunar payloads to the surface of the moon.
It is a delivery service, akin to a delivery service that you'd have here on Earth.
NASA will provide payloads to a commercial company. They decide how to get it to the moon. They have to develop their own lander, but they also have to manage the entire end-to-end mission.
It's meant to provide affordable, rapid, frequent access to the lunar surface through American companies.
We're funding different companies.
We have commercial companies that are competing to win task orders to deliver our payloads to the surface of the moon.
One of the goals when we started CLIPS was to help establish a lunar economy.
Somebody has to do it first, and then it becomes commercially available. Then they're able to crank them up. Then they're able to make it more affordable. And so the lunar surface is just the next frontier for a commercial environment.
But we had to acknowledge up front, all the way through the highest levels of the agency leadership, that some of them will fail. These missions may not be as successful as a traditional NASA mission.
We have accepted the risk that going through this innovative approach with these commercial companies, that there could be some failures. Some of them are new companies. None of them have ever successfully landed on the surface of the moon. So they're going to learn lessons.
We need to give our vendors the opportunity to learn.
And so that'll help ultimately buy down our risk as these companies learn, okay, what does it take to actually build up the lunar lander, integrate payloads, get to the lunar surface and land safely.
They've been able to demonstrate that they have very, very good technical depth and the ability to design and execute missions. We're willing to take more shots on goal. And we aren't risking human lives. And in the big picture, if we're flying missions at 1/10 of the cost of a NASA mission, and we fail 2 of them, we still get 8 missions for that same price.
Even with 1 or 2 or 3 failures, this is still a very economical proposition. It's a risk posture which is more risk tolerant than NASA is accustomed to. There's not a single one of these companies that's willing to bet their mission on a coin toss. Every one of them is doing what they can in order to have the most successful mission possible. But the important thing to realize is that risk tolerant does not mean risky. And the rewards are a long-term ability to get payloads to the moon inexpensively, frequently, and rapidly.
We want science, so we can then put more of our resources on even more science, exploration, and technology payloads and get more of a return on investment when we get to the moon.
CLPS provides tremendous benefit across the scientific and economic communities.
So there's a lot we'd like to learn about the moon to help human habitation and prepare us for missions to Mars and beyond.
So the moon is the first step.
The teams here in Nova Control have been working diligently over the past 7 days to take us this far and are laser focused on the operations ahead. We're following the clock down to the start of those autonomous operations of Nova-C, starting with the powered descent initiation. For now, we're heading back over to Leah Cheshire, who's standing by with NASA's Associate Administrator. Leah.
Thank you, Gary. I'm joined now by Jim Free, NASA's Associate Administrator. Thank you for joining us, Jim.
Thanks for having me.
This is a big day, and what are some of the challenges to landing on the moon that people might not expect?
Well, it is a big day, by the way. You're right. I think the challenges are multifaceted. First, getting into lunar orbit is a challenge. Going to the South Pole is different than going to other parts of the lunar surface. The lighting conditions are a lot different than at the equator. So you have your hazard detection has to be a little more reliable. You have to be able to do that last minute avoiding of the hazards that are on the surface and finding that right place to set down, so you're also level or within a tolerance that you can be for level on the surface.
We've talked a little bit about how this is a different model for us. So how does NASA help ensure success while we also allow these companies to figure out their solutions?
We're able to offer our technical expertise, so companies can ask for technical experts from NASA that might be an expert on lunar surface conditions or orbits around the moon, or even just in assembly of the spacecraft, the vehicles. But they can also ask for help during the mission. We provide help through our deep space network to get the communications, to bring the data back to the control center here, to help them maybe understand their orbit better or get more communication with the spacecraft as well. So both in advance of the mission and during the mission also.
And CLPS is just one way that NASA is using, we're working to strengthen the American space economy. So what are some other ways, and why is NASA pursuing this commercial route for complicated space missions?
So we started back in the space station, where we started with the commercial cargo, where we spurred on investment in commercial delivery of cargo to space station. That's ported over into our crews flying commercially. We're doing that on the Artemis program, buying things by service so that we can spur on other investment that allows us to get our resources and use them elsewhere to do other parts of our mission, exploring the moon or beyond.
You talked a little bit about Artemis for a second. So how does CLPS fold into NASA's plans with Artemis and with this Moon to Mars architecture?
I think I could talk about Artemis for hours. But CLPS is absolutely essential for Artemis. It's our first steps of understanding the lunar environment. So the Intuitive Machines lander is going to help us understand how the lunar dust moves as the rocket plume, the exhaust of the rocket hits that dust. We need to understand that because we're going to land even bigger landers with our humans in the future, and we want to land it close to our other elements, so we're not blowing that dust everywhere. How does it behave? So that's just one part of it, but it is our first step of understanding that environment that we're going to put our astronauts on the surface.
And of course, we're really, really looking forward to that mission. But for now, thank you so much for joining us here today. We are going to go back to Gary and Josh to highlight some more payloads ahead of the powered descent initiation.
Hey, thanks, Leah. A report at 4:54 p.m. Central Time from the flight control teams shared that Nova-C is less than 30 kilometers above the lunar surface and is in the lunar southern hemisphere. We're still on track for PDI at 5:11 p.m. Central Time. Nova-C will perform this maneuver to slow the vehicle's descent, then pitch over and scan the landing site for hazards, making any necessary corrections in the final burns to ensure a safe landing. We've highlighted 5 of the 6 NASA payloads so far throughout our broadcast today. Let's talk about the final NASA payload, LN-1. Lunar Node 1, or LN-1, is a small CubeSat-sized flight hardware experiment that integrates navigation and communication functionality for autonomous navigation to support future lunar surface and orbital operations.
Lunar Node 1 is meant to be a demonstration of how we can use various navigation technologies to figure out where you are in and around the moon. I'm holding in my hands the Lunar Node 1 mass simulator. We use this build to test out our vibrational modes, put on a shake table, and also do fit checks with the lander itself. Inside of our payload, we have multiple electronics boards that fit within this chassis that is a little bit about a half a U in size. You can see our external connectors here where we have our data and power to the lander itself. And within here, we have multiple boards that do the power regulation, our data control, our FPGAs, all those kind of electronics pieces are in here, as well as a small S-band radio that attaches up underneath this top radiator in order to distribute this heat, and then to talk to the antenna, which mounts here. This is the same size and build as the flight payload. It's just not covered in MLI or some of the other materials that you'll see on the flight build itself.
LN-1 will test a lunar navigation concept of operations with the implementation of MAPS, or the Multi-Spacecraft Autonomous Positioning System. Ideally, this kind of technology can support a network of communication and navigation amongst local surface and orbital operations. LN-1 will test multiple navigation links from the surface of the moon back to Earth to characterize both MAPS transfers as well as GPS-like signals that could support a future lunar communication and navigation network.
Gary, one of the best things about communication and data is getting imagery back. And Intuitive Machines has several camera systems on board, including EagleCam. It started as a challenge from our CEO, Steve Artemis, to his alma mater, Embry-Riddle Aeronautical University. Students and faculty created EagleCam to take an out-of-this-world selfie of Odysseus landing on the moon. The camera system could capture the world's first ever third-person picture of a spacecraft making an extraterrestrial landing. The camera system is designed to deploy off of Nova C approximately 30 meters above the lunar surface and take images of Odysseus during landing. Additionally, the device will test a dust removal system, which could lead to the future advances in spacesuit technology. As part of this project for EagleCam, Embry-Riddle teamed up with NASA's Kennedy Space Center to demonstrate the NASA-developed electrodynamic dust shield, or EDS. EDS uses an electric field to remove dust. The technology was tested aboard the International Space Station and will be the first ever demonstration of EDS technology on the lunar surface after landing. Intuitive Machines also had several cameras on the lander, including wide and narrow field of view cameras. They started the mission with incredible imagery as the SpaceX second stage deployed our Nova C lunar lander, capturing iconic images of the Earth after separation. It requires a lot of planning, work, and just a hint of luck. Payload integration managers programmed the lander's wide and narrow field view cameras to take 5 quick images every 5 minutes for 2 hours, starting 100 seconds after separating from SpaceX's second stage. Out of all of those images that were taken, we ended up with just 4 inspiring ones to show humanity's place in the universe. And right now, we're a little more than 10 minutes from powered descent initiation. Let's go to Leah Cheshire one last time for the final interview ahead of this critical maneuver. Leah.
Thanks, Josh. I'm here now with Nikki Fox, NASA's Associate Administrator for the Science Mission Directorate. Thanks so much for joining us.
Thanks for having me. This is a great day.
It is a great day, and you're watching this with leaders from NASA and Intuitive Machines, just very close to here. What's happening in the room right now just before these final descent maneuvers?
Oh, there's just excitement, anticipation. Everybody knows landing on the moon, going to the moon is hard. And we're already celebrating because this mission is already a success. We've launched, we had a beautiful launch. We've taken great science data all the way, every single challenge. The team has really risen up and solved it. And now we're in lunar orbit, minutes away from starting our descent down to the lunar surface. So for me, so many successes with this mission already. So just a lot of excitement.
I'm loving that. So we are working with these American companies in a very unique way. These are challenging goals, and some people would probably consider this a bold endeavor. But what does it mean to you when you look at pursuing challenges in a bold new way?
I mean, you're right. It is bold. It is a new way of doing science. It is a partnership with totally new companies who haven't done these things before, and we are partnering with them, and they are taking our science. It's a way for us to get more science and more technology to the moon quickly. So it's faster. It's very cost effective. It's very efficient. We're on our way. We've got the 6 payloads from NASA, and we're excited to get them down there. With every new thing we do, there's always a challenge, there's always risks. This is a high risk but super high reward, and it'll get tons of science on the surface. And for my NASA science, this is exciting because our Artemis missions and our lunar science touches all 5 of our science divisions in very profound ways. So super excited.
You said high reward, so I want to talk for a minute about the valuable scientific insight that we can get from the moon. What is that? What does it mean for NASA?
I mean, there's so much we can do on the moon, particularly where this one is going down to the South Pole. We think we're going to find great volatiles down there. So as we get prepared to send our astronauts there, then we know that there's water there, and we can use that water. Water's very heavy to carry, so it's really great if you can use it on the moon. We can break it up into hydrogen and oxygen, use it for fuel. Really great for our sustainability, but also where they're going is one of the oldest regions of the moon, about 3.85 billion years old. So we can actually learn about what our solar system was like before life started. Life is very noisy. We're very, very noisy here on Earth. The moon is just like pristine, and so we can really do some amazing science.
I look forward to learning more about it. So any final words before we wrap it up?
Just thank you. I mean, literally, thank you. This is such an amazing team. Thank you to the people that put the science and the technology experiments on with us, those teams. Thank you to the commercial teams that put their instruments on and are riding with us. Thank you, of course, to Intuitive Machines for this just beautiful, beautiful lander. And thank you to SpaceX for a beautiful ride to space. It's such an incredible effort. All one, I don't know, I'm a big bundle of emotion. Go NASA, go Clips, go Odie, go Intuitive Machines.
I'm with you all the way. Thank you so much for joining us here today. Now we are following Intuitive Machines flight controllers during Nova-C's final descent. So back to Josh and Gary.
Thanks a lot for that, Leah. During that interview for folks at home, we did hear that there was a maneuver to burn attitude, which means the lander is starting to make the positional requirements needed. And we're going to start listening into the IM-1 channel so folks at home can hear. We just heard from flight controller about 5 minutes until TIG.
Altitude of 10 kilometers, downrange 1,100 kilometers.
TIG being time of ignition, so we're inside of 5 minutes.
TIG minus 5 minute dead pins.
TIG minus 5 minutes. We are standing by for powered descent initiation. Gary, this is a critical 11-minute burn to slow the lateral velocity such that Nova-C can pitch over for further operations. And while we were in that interview, we did hear that the main engine gimbal checkout was completed. So now we're focused on the operations with Nova Control. For folks at home, we are listening into the live channel there.
That's right. A lot's happening in Nova Control. We're going to be hearing these status calls periodically as we follow the flight control teams that are monitoring Nova-C's descent towards the lunar surface. A lot's happening, Josh. Of course, we have this 11-minute burn. We're focused on the propulsion elements of this PDI. At the same time, the spacecraft is oriented in such a way that it can use a technology called terrain relative navigation to scan the environment along the way. What's happening there?
Right, so we know that we needed terrain relative navigation then when we were descending and coming down to the lunar surface. Now, this involves 2 pieces. You have a camera and you also have a laser rangefinder. At the top of the show, we started talking about, hey, the laser rangefinder that Intuitive Machines put on Nova-C, it's not operating. We made the decision for flight controllers to utilize 2 of the laser beams from NASA's NDL payload, make the software patches required to reassign those lasers into the TRN and HRN cameras in order to give us an opportunity to land on the south pole of the moon today. Gary, is quite the feat and challenge overcome in just about 2 hours because we elected to delay that orbit and go into another orbit. That's why the show was a little bit later. appears to be paying out. The last call-outs that we heard, Gary, were talking about beginning processing optical images, and that was nominal. The last time we heard that was just about 20 minutes ago.
The status checkouts of these critical systems are essential to understanding the performance. The folks you see now on your view, this is Nova Control. They're monitoring every step, all the data coming from Nova-C ahead of PDI, which is scheduled just a little bit after 5:11 p.m. Central Time. Exactly what are these folks looking at, Josh?
Well, right now everyone's looking at their assigned screens, and all of them are tailor-made. Generally, there's a few who are looking at the same type of screen, but they're tailor-made for their task. You have Spark looking at electronics, things like how hot are the electronics. Payloads are monitoring different parts and pieces.
5 degrees to burn attitude.
5 degrees left until burn attitude. The vehicle is still getting ready for this PDI ignition, which we expect here in just about 2 minutes, Gary, two minutes. So everyone's looking at their screens and doing their respective jobs and reporting up into the mission director, while the activity director is keeping in touch with everybody and making sure we're putting this whole thing together.
Press started.
There's a call for tank press started. Just a little bit before that, Gary, we did hear that they were working on the cryo fill. So these are all steps that are leading towards PDI, powered descent initiation. We expect that to take about 11 minutes, where we're slowing Nova-C's velocity approximately 1,800 meters per second, and that's required to get this lunar landing opportunity in just a few minutes.
90 seconds to TIG.
Propellant tanks at flight pressure.
All right, 90 seconds until we begin that propulsive maneuver. Again, power descent initiation is about a 10 or 11-minute burn that will slow the spacecraft's descent. A lot's going to happen after that 10 minutes, Josh. This is a single continuous burn. After that, we're going to see a lot of events in rapid succession: pitch over, vertical, and terminal descent.
And we just heard another call out from the prop console saying that feed line prep is complete. What that means is Nova-C's propulsion system, that mixture of liquid methane and liquid oxygen, that feed line is prepped, getting ready to go into an injector to blend those two propellants, and the propellant and the oxidizer, and have ignition of PDI. We're tracking that in just under a minute, Gary.
Converging on burn attitude.
Lander is getting into the correct attitude required.
Line prep complete, both sides.
Another call for feed line prep complete for liquid methane and liquid oxygen in preparation for this PDI burn.
"15 seconds, exec mode."
15 seconds to exec mode. We're tracking a little less than a minute, though, until the time of ignition for power descent initiation.
Settling. Ignition. Throttling up. Main stage.
There we heard main stage ignition. That's coming from our prop console, Rob
Good
Moorhead.
control.
GNC call on good control.
Thrust to weight 1.5.
These are great call-outs in between our prop console and our flight manager, Scott Tamblin, calling it as the data is feeding into the lander, which means we are continuing to have good communications. The lander is sending that back to flight controllers in Nova Control. Gary, something we prepared for, we planned on, is that loss of communications, and that's why we have this.
I see good thrust control.
It's a good thrust control call from prop, but that's why we have this autonomous lunar lander. You know, we know that, hey, we want to light PDI in this moment. These are the steps you need to get there. But from here in, this is an autonomous lunar lander, and flight controllers are monitoring communications and tracking the progress right along with the public right now with us.
Nova-C has the helm. It is in control and is making the decisions necessary to ensure a soft landing. We heard call-outs about thrust, full thrust right now. There is the ability to throttle that thrust, and we'll see that throughout the descent as the fuel tanks continue to unload and we expel that propellant.
And we did have a few questions come in about how much gas are we giving this to slow down the vehicle. And we want to remind folks that this PDI burn goes...
Commanded thrust 90%.
Goes in just about 90%, right on time. So it goes in at 90% in order to, if the lander makes a decision and says, I need to slow down more and make a decision to make a safe landing, it's able to add a little bit more oomph and make that decision a reality rather than just a possibility.
Fido, I'm showing 500 kilometers to target, but my display's a little bit stale.
That's the mission director, Tim Crane, calling about 500 kilometers, but stating that his information might be just a bit stale.
1,000 psi in the helium tank.
It's part of the reason we're showing this animation, Josh. Of course, this is not telemetry driven. We're just showing you exactly what's happening. As we hear the calls, this information is relayed through the audio loops. Not enough bandwidth to do a live stream of this, so we're relying on the data that's being fed from Nova C to Nova Control.
Yeah, that data is going into the flight controllers, and what you're seeing on your screen right now is just to give you an idea of the vehicle's attitude. You heard them talking about moving to a burn attitude. This is what we expect Nova C is doing right now. It is a simulation in the large screen just to give you an idea of what's happening over these critical approximate 10, 11 minutes of PDI, powered descent initiation, trying to slow Nova C down, bring that acceleration down to about 1,800 meters per second. And there's some follow-on steps after that, Gary. It involves pitching over the lander using that gimbaled engine. We heard the maneuver to burn attitude followed by main engine gimbal checkout. So they'll use that gimbal to pitch the lander over and start a vertical descent. This is where we start getting a little tricky as far as there is a final approach. It may add a few seconds, it may add a little bit of time, but we are intended to land right around 17:24. That's 5:24 p.m. Central Time. But know that there is some give and take. We're also expecting, plan for, and train for a little bit of loss of communication during this process.
That's right. And that communication is absolutely important. And part of the reason, and we've been stressing this, Josh, is the autonomous operations of Nova C. Part of that is after it performs that pitch over maneuver.
400 seconds to go and braking 1. Good control.
Fido, I see TRN depause processing in flight.
All right, that was the call that we were waiting for. That was our major problem we've been working on in this dynamic situation, is getting those images processed from the HRN camera, TRN camera, which in this case, a dynamic situation, we had to improvise a little bit and reach into those 2 laser beams from NDL, figure out a patch while we were in lunar orbit, just about 2 hours, and it sounds like we are getting good readings from those images. Absolutely remarkable feat. We also happened here, I think it was 400 seconds remaining. That was coming from Fido and Flight Dynamics. Sean Stewart working the console this evening.
This is excellent calls to hear. Hazard relative navigation is going to be used after the pitch over maneuver. This allows Nova C to make some decisions and scan the landing site underneath it and make decisions in an area that calculates the terrain to make sure that it's landing in a safe landing zone.
Right, so we finish up PDI, pitch over, and we have to use that hazard relative navigation, a critical tool in order to land on the moon, to make those decisions, right? There's no human eyes, human elements deciding, okay, I see the hazard, I need to steer this way, or maybe press the gas, press the brakes. This all happens autonomously, and this is a huge requirement and a great call out to hear about the HRN camera system and processing those images. Right now, I am tracking 5:16 p.m. We expect PDI to go until about 5:21, 5:22.
300 seconds and braking 1.
Or about 300 seconds to approximate those numbers.
Very precise. Josh, after those final series...
Thrust to weight is 1.7.
Following along, after those critical maneuvers...
Committed thrust still 90%.
90% thrust. We'll hear those call-outs periodically. We started at full thrust, 90%, still throttling.
Nominal.
And good performance on that engine.
That's a great call out. Two things there. Nominal performance on this engine as well as the helium tank. So what we haven't mentioned so far in the show is that the helium tank pressurizes that liquid methane and liquid oxygen tank. But in addition, it's also used for reaction control system. Those are the small spurts that you see at the top of the lander in the animation that control the vehicle's attitude. So for things like landing on the moon, you really want to land at the right attitude. That way your antennas are facing back, direct line of sight to Earth, and you can get that ultimate confirmation once you do suspect that you have landed on the moon.
The antenna alignment is an important element of landing on the moon, Josh. We're expecting the high-gain antennas to be pointed towards Earth to confirm, but there may be a delay.
We are expecting some sort of delay. I had just talking to the mission directors about how quickly we could receive a positive confirmation after this landing process is through, and there was some dispute over how long. The earliest was just about 15 seconds after we see timing of when the event is supposed to happen. So right now we're tracking about 5:24 p.m. Central Standard Time. So maybe anywhere from 15 seconds after that, maybe a few minutes, 2 to 3 minutes while we work to acquire that signal. Because as you mentioned, the lander is going to a general area.
9 kilometers altitude.
9 kilometers altitude call from Tim Crane. The lander is going into a general area that we say, this is the general area we want you to fly to. It's using that hazard relative navigation to make better decisions about this is an area with the least amount of slope. This is an area that's free of boulders and other obstacles. So it's making autonomous decisions about where to go.
3 minutes to go, breaking 1.
3 minutes call. Just to wrap that up, when the lander is making those decisions, Gary, it's also very difficult to track. We've been very fortunate thus far tracking communications to this point.
To wrap that up, Josh, 3 minutes, that brings us to just shy of 5:22 p.m. Central Time. We should hear that the power descent and initiation burn is complete. Then we'll begin the next series of maneuvers to get us towards vertical and terminal descent. It starts with pitch over.
And just looking at our notes here, we did go into this burn expecting pitch over at 5:21 and 57 seconds. So good call out on the timing of that maneuver. It's important to remember PDI starts an engine burn that does not stop until landing. So this is a throttleable liquid methane, liquid oxygen engine. We lit the engine at PDI, and while we are changing into a pitch over, vertical descent, and terminal descent and then landing, that is a throttle down to the lunar surface. And when we do get out of PDI, if we hear that call of PDI complete, good burn, everything after that is going to happen in very quick succession, Gary. The time it takes to go from pitch over to landing, or what we estimate landing to be, just looking at maybe 90 seconds is what we expect nominally.
3 minutes to touchdown.
There is some wiggle room. 3 minutes to touchdown call from the mission director.
For an on-time landing, that sets us a little after 5:23 p.m. Central Time.
Right, our notes going into this burn, 5:23 and 25 seconds.
The autonomous operations, Josh, sets this to a clock. This is exactly what we got relayed before the start of our
Still
coverage
processing.
today. We're right on track.
DPAS, terrain relative navigation measurements.
Excellent call out. That solution that flight controllers were working so hard on to make sure HRN was working, pulling on extra resources that weren't originally planned for from those 2 laser beams from NDL. It appears and sounds like that solution is working, and the people working to patch that software were certainly under pressure. The clock was ticking as we went into that extra lunar orbit. It wasn't a situation where we could just sit in lunar orbit and try to solve our problems indefinitely, and it's sounding good so far on the call outs.
2 minutes remaining till touchdown.
2 minutes to touchdown. That required a patch to be designed on the ground and uplinked to Nova-C to confirm that those laser sensors on NASA's navigation Doppler lidar could be routed to the terrain relative navigation and hazard relative navigation. That call out is fantastic.
Friday, do you have an altitude reading?
Standing by to see if we can get an altitude reading from FIDO here. That's Flight Dynamics Officer Sean Stewart on Blue Team.
confirm that looked like a pitch over gimbal.
Let's do it.
Sounds like we have some data that confirms pitch over. This starts the HDA process. That's hazard detection avoidance. Throughout this show, you've heard Gary and I talking about the problem that was attempted to be solved in lunar orbit, making the decision to not only postpone this show.
NDL indicates altitude of 1,000 meters.
1,000 meters call out from NDL. That is coming from flight management. This is a system right now. NDL was not intended to be the primary landing system on this. Instead, we're using 2 laser beams from NDL and feeding that into that hazard detection and avoidance system that you see on your screen right now, with the lander making autonomous decisions about where it wants to land. That is generally
less than 1 minute remaining to touchdown.
Less than 1 minute remaining for touchdown.
And again, that's the time of touchdown. It may take some time to actually confirm the status of the lander.
And in this process, we do have a deployment of Eagle Cam attempting to take the third-person images of Nova C going down to the lunar surface. We are inside of 1 minute, Gary.
Yes, we're well into blowdown.
And we're tracking here in the broadcast booth. The clock has reached the expected.
May take a minute for comms to reestablish. Stand by.
There it is, mission director beating us to it. We've reached the expected time of landing, but now is the process of waiting for comms, and we are in standby mode, as you heard it from the mission director, Dr. Tim Crane. And 1 minute has elapsed from the notes that we have, Gary, of that original burn starting at PDI.
And you have carrier lock.
That's MD asking if we are getting the ground stations locked on to Nova C. That carrier lock call, Gary, we expect that to come from GroundNet or COM. That conversation possibly not happening on our public channel that we have access to. We're just standing by to hear that come through the channels as we approach almost 2 minutes since we estimated the landing time. We did get a few call outs on the side, folks coming into the room saying there was about a 2-minute forgiveness in our timetables.
We are checking our antenna reception.
Checking antenna reception. And we're standing by, Gary. We're standing by just as we approach 5:26 p.m. Central Standard Time. Given those mission directors' notes of the flexibility between what we were tracking, what we were given was just about 5:24.
All stations, this is MD. Please look back through your logs and confirm the last information you had, and we'll determine this is a comm outage.
And that's the mission director, Gary. These are our notes here of what we believed. We talked about the comm outages with the lander making autonomous decisions. This is the process of going through the last bit of data that came into Nova Control and working to verify, okay, this is the last bit of data. Where was the lander possibly going? How do we look for it and establish those communications? Nova C uses 4 antennas placed at the top of the lander that are designed to capture these communications. But we did expect this. We talked about it, that this is a communications challenge in it of itself, and right now we're standing by to hear that communications call out.
We're just a little more than 3 minutes from the time of the when the clock reads 0 for Nova C landing on the moon.
And we just checked with our team here in the broadcast booth, decided to let's stay on this. All the chatter we are not hearing on this public channel, Gary, all things indicate that we are working to solve a possible communications challenge in this moment. So we're going to continue to stand by.
For those following along.
MD Prime on IM-1.
Go for Prime.
Yeah, I guess you polled the room looking for states, and we're going to go ahead and cycle the ground transmitter on Goonhilly and do some RF sweeps. Is that your plan?
That's correct.
Roger, copy.
And that's just what we had in mind in our notes, Gary, is that if we encounter a communications challenge, we mentioned how difficult it is to land on the moon and continually have those communications. What you just heard there is folks talking about using the Goonhilly Earth Station Limited dish in the UK to do a sweep looking for that signal. We mentioned that autonomous process of the lander reassigning itself somewhere that it believes is safe. Going into it, we heard that the HRN camera was functioning and able to make those decisions after what was a 2-hour orbit of problem solving with Intuitive Machines' TRN and HRN cameras. The laser rangefinders assigned to those are the ones that Intuitive Machines installed inside the navigation pods. The laser rangefinders were not activated. We went to NASA and asked to use 2 of the laser beams on the navigation Doppler LiDAR.
That's right.
And spent 2 hours in orbit.
Team, we're going to confirm our pointing vector with our antenna for post-landing.
Yep. We spent about 2 hours in orbit to solve that problem. We got good readings on the way down. And right now, we are working to confirm communications on the surface of the moon, roughly around the Malapert A region. That is the South Pole region of the moon.
That's right. What we do know is the powered descent initiation. We were following along in the status calls. We executed a pitch-over maneuver, and we're counting down the clock to a landing time of 5:23 p.m. Central Time. Well, Josh described those processes of working on the communications component to confirm data from the lander, pulsing the teams surrounding him to check the status of Nova C and the data that they were receiving here in Nova Control to confirm landing. And part of that, Josh, as you described, is communications. We're standing by.
Fido MD on IM-1.
QMD.
I'm looking at our phase plane there for the last part of the flight. Looks like we had excellent pitch and yaw control throughout, but I did see a little bit of a roll excursion. Could it be that we landed off angle and roll in the final phase?
So I do see we had up to an 8-degree excursion. We're about to begin the roll maneuver, which is about
terminal phase.
The terminal phase, which is a large roll maneuver to get to landing attitude. That's the last data point I have. But up until that point, we were really solid.
Right. So terminal phase begins at 30 meters. Or post HDA.
Post HDA.
Post HDA.
400 meters.
Very good.
And that's a great conversation confirming.
That's good ground network. Good for box scan. Make that go.
Yeah, that was good confirmation of the process that we were very familiar with, talking about the attitude of the lander, making sure that those antennas are within direct line of sight with Earth stations, ground stations on Earth, excuse me.
Mission director at all stations are also updating our pointing vector with our dishes to make sure that they're tuned in on our final landing site.
There's a call. We're searching for that communications back to the ground station. This one particularly is in the UK that's tracking us. And it's important to note, Gary, that we have an entire network dedicated to working these communications problems. It's been active this entire mission. And the largest, most powerful dish out of all of them is about a 64-meter dish in Australia. That time to search with that opportunity with the largest, most powerful dish, we're looking at about 12 to 13 hours after our estimated touchdown. So this is a process that we could be looking and searching for the lander's signal for confirmation for quite some time, but we're going to continue to listen in and stand by as our flight controllers are working with the ground station in the United Kingdom to work this issue, work this problem. It's another challenge, very similarly to the challenge solved just to make it this far.
Signs of life, we have a return signal we're tracking. We have an onboard fault detection system for our communications that after 15 minutes with lack of communication will power cycle the radios, and then after that for another 15 minutes it will then switch antenna pairs. So we have some time here to evaluate. We do have signal that we're tracking, so we'll see what happens.
There's a great call out about the autonomous systems installed on our Nova C-class lunar lander named Odysseus. The process he's mentioning, Gary, is very similar to the one that we were preparing ourselves for at AOS, to where the lander has systems in place to recycle its antennas, to switch antenna pairs, and that was very similar to what we thought we were going to need to do after acquisition of signal. When we separated from the second stage of the launch vehicle, if we made it to a certain point, the lander was autonomously programmed to start taking matters into its own hands, and that was the information that our mission director, Dr.
We're not dead yet.
We're also not dead yet.
And the key here, Josh, is patience. It's 5:34 p.m. Mission Director Tim Crane confirming that it could take 2 phases of 15-minute increments to confirm the status of the landing. So we could be here, and we'll stand by and monitor as Nova Controls continues to work this issue.
Yeah, tense moments inside of Mission Control with the most qualified folks.
We're picking up a signal from our high-gain antenna and transmitter. It's faint, but it's there. So stand by, folks. We'll see what's happening here.
All right, we're going to continue to stand by. Let's keep this camera on inside of Nova Control. It sounds like we are getting some kind of faint signal.
I want to send a series of commands to reactivate, make sure we're transmitting to keep the Quasonics active.
We're still standing by. The last call from Mission Director Dr. Tim Crane was that we were getting a faint signal from Odysseus's high-gain antenna.
All stations, this is Mission Director on IM-1. We're evaluating how we can refine that signal and dial in the pointing for our dishes. What we can confirm, without a doubt, is our equipment is on the surface of the moon, and we are transmitting. So, congratulations, IM team. We'll see how much more we can get from that.
An excellent call from our mission director, Dr. Tim Crane.
IM-1.
And over to our
Prime.
CEO, Steve Artemis.
Yeah, if I could just pass on a few words to the entire team in Intuitive Machines at SuperBab and here in the Mission Control. What an outstanding effort. I know this was a nail biter, but we are on the surface and we are transmitting. And welcome to the moon.
Houston, Odysseus has found his new home.
An excellent call, and this is our team of Intuitive Machines mechanics and their families, their friends, everyone who has sacrificed so much to make it this far.
Stations.
How about that call, Gary? That was something else, a faint signal. Now it's time to work on refining that signal. But Dr. Tim Crane, our mission director today, making the call. Odysseus has a new home.
It shows the disciplines of the flight controllers in Nova Control. They waited until there was absolute confirmation that there was a signal, and then that was when they took the moment to celebrate. We saw that it wasn't just the individuals in Nova Control that contributed to the mission. The contributions to enable the success of Nova C's landing on the moon stretches far and wide. We showed, of course, some of the folks watching there, but really it extends even farther than this. A wonderful and truly amazing moment to celebrate. The U.S. has landed on the moon once again.
And to everyone, you mentioned it goes beyond just the folks that we saw on camera waiting and working through those tense moments, but their friends, their families, and everything it took to get to this point. We're still expecting an image. We expect that to come down sometime in the future, especially as we look towards some high-resolution images. Let's go ahead and it sounds like we do have a message we'd like to cut to. Can we have that message special for our folks, our employees, and folks watching at home?
Hey, that's right. With Nova C landing at Malapert A, congratulations, like you said, Josh, are flooding into the teams that made this happen. Really sets a tone for the American leadership and the future of a strong lunar economy. So here's NASA Administrator Bill Nelson.
On the 8th day of a 250,000-mile voyage, a voyage along the Great Cosmic Bridge from the launch pad at the Kennedy Space Center to the target of the south pole of the moon, a commercial lander named Odysseus, powered by a company called Intuitive Machines, launched upon a SpaceX rocket carrying a bounty of NASA scientific instruments and bearing the dream of a new adventure in science, innovation, and American leadership in space. Well, all of that aced the landing of a lifetime. Today, for the first time in more than a half century, the U.S. has returned to the moon. Today, for the first time in the history of humanity, a commercial company, an American company, launched and led the voyage up there. And today is a day that shows the power and promise of NASA's commercial partnerships. Congratulations to everyone involved in this great and daring quest at Intuitive Machines, SpaceX, and right here at NASA. What a triumph! Odysseus has taken the moon. This feat is a giant leap forward for all of humanity. Stay tuned.
All right, thank you, Administrator Nelson. Again, Nova C and the United States has landed on the moon at 5:23 p.m. Central Time today, February 22nd, 2024. Congratulations to Intuitive Machines on the successful landing. Science and data gathering is already underway and will continue for roughly 7 days on the lunar surface, activating payloads and gathering important scientific data to help ensure future successes in Artemis missions. For more about NASA's CLIPS initiative, visit nasa.gov/CLIPS.
Gary, it's been quite a journey for all of us at Intuitive Machines. Thanks to NASA for the continued support to enable today's successful landing, and of course, everyone at Intuitive Machines, their friends and family who made all of this possible. That will wrap up our coverage of Intuitive Machines' IM-1 mission. Thanks for joining us.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.